Hello, in this video we want to show you just one of the experiments for the GUNT thermoline unit for heat conduction in metals. This video follows our introductory video about the GUNT thermoline series of equipment. If you haven't seen it, make sure to check it out first. This video will cover the following parts: theory, setup, experiment, and evaluation. Also, if you want to follow our experiment demonstration more closely and want to get a better understanding of the theory, you can use our GUNT e-learning course, which we will show you parts of later in this video. With thermal conduction, which we want to demonstrate in this experiment, heat or energy is transferred by direct interaction between molecules, molecule collision that is, within a solid or fluid at rest. The driving force behind this is a temperature differential within that substance, or two substances of different temperature which are in direct contact with each other. This transfer of heat can occur in all aggregate states: solid, liquid, or gas. The amount of heat that is transferred depends on four different factors: the thermal conductivity, which is a material property, the heat conducting length, the heat transferring area, and the temperature differential between the two ends of the thermal conductor. The WL420 is designed as a benchtop unit. Here we have the base, which contains all the electronics necessary for the sensors and the connectivity to the PC with the GUNT data acquisition software. It is important to point out that the PC is necessary. The actual experiment is located on top of the base and happening here on the left. The WL420 comes with a specimen for 5 different materials in 2 different lengths respectively, as well as one specimen with constricted cross-section. The specimen is placed in this spring-loaded device, which ensures reliable contact of all heat transferring surfaces. Here we have a heater of approximately 30 watt, and at the bottom, hidden in the base, is a corresponding Peltier cooling element with 50 watt capacity. Here you can see the cooling grill for the Peltier element, and it goes without saying that this should not be covered. And finally, we have 2 thermocouples as temperature sensors, which are placed at either end of the specimen. What you cannot see are 3 additional temperature sensors, one in the top measuring the temperature of the heating element, one in the bottom measuring the temperature of the Peltier element, and one at the back of the base for measuring the ambient temperature. When conducting experiments with a unit for the first time, a calibration is necessary. The aim of the calibration is to determine how much of the electrical heat is lost through convection and not dissipated through the specimen as conduction. Let's have a look at how we set up the unit for this process. For the calibration process, the spring-loaded device is locked in the upper position without a specimen. This way, all the electrical heat is dissipated via convection. When starting up the software which is supplied with a unit and installed on any Windows-enabled device, you can select one of 4 languages. For the calibration process, you select calibration from the test menu. The next step is to tare the sensors. This is done to compensate for any slight measuring errors or inaccuracies between the sensors. As you can see here, the temperatures shown are slightly different. By pressing the tare button, the values for the temperature measurements are numerically equalized and show, for the moment at least, the same value. The tare function should only be carried out after the unit has completely assumed ambient temperature and when possible in an environment without any disturbances. Now the output of the heater is set to a value of 25% maximum capacity, which is equal to 5 to 6 watts. The data logger is selected from the modules menu, and after the corresponding window pops up, measurement is started with the on-off button. You can see from the increasing number in the counter here that the logging of measurements is in progress. Now you can select chart recorder from the Modules menu and a new window pops up showing you a chart with real-time measurements. In the chart recorder, you can select the values to be shown. You can also choose style and color of the individual graphs, and you get context menus when hovering the cursor over certain areas of the chart. Note that the loss through dissipation is recorded and a correction factor K is calculated and stored. This is used for all consecutive experiments. For the purpose of this video, we will show you only one of the experiments for the WL420. For a full list, please check out the manual on our Thermoline website. In this experiment, we will determine the thermal conductivity lambda of a given material. When placing the specimen into the spring-loaded device, we recommend using a small amount of the supplied heat-conducting paste. Then we insert the two temperature probes into the respective holes in the device, like so. Let's start measuring. After setting the appropriate values for heating and cooling, you can observe on the chart recorder how the values for the measured temperatures change. You can also see in the system overview these temperatures as numerical values together with the calculated heat conductivity lambda. Make sure you select the correct specimen length, otherwise the results will be incorrect. After a while, a steady state is reached. As a tip for teachers, you can deselect the display of the value for lambda to task the students with calculating it themselves, just like in the old days. The aim of the experiment was to determine the value for the thermal conductivity lambda for aluminium. With the measured values for the temperatures, the transferred or conducted heat, and the length and diameter of the specimen, we can calculate lambda in the following way. The formula for the heat flux shown here can be rearranged as an expression of lambda like this. When we insert our actual measurements from the experiment in the formula above, the result is a value for lambda of 184 watts per meter Kelvin. Within a reasonable margin of error, this is pretty much in line with the values for aluminium typically found in technical literature. For the purpose of this short video, we have only shown you one of the many experiments for the heat conduction unit. Other experiments include, but are not limited to, variation of specimen length, sample with recess and cross-section, calibration of the unit including tearing of the sensors, combined heat flux, function of the Peltier element, or, as you can see here, stacking of two specimens for different materials in order to determine total thermal resistance. We hope you enjoyed this video showing just one of the experiments for our WL420 unit from our Thermoline series. For more information, visit our website www.gunt.de. If you have any specific questions about our Thermoline series, or if you want to discuss further laboratory needs that you might have, please contact us.